When we were talking about the generating function of the Hermite polynomial, you probably wondered where this very funky looking exponential came from. It just seemed to fall out of the sky, right? Now, what we're going to show in this exercise is that you can actually calculate the form of that generating function. The price we pay for that is, of course, a different set of assumptions. The assumption here is that we know the differential equation and that we somehow managed to solve that differential equation to also calculate the recurrence relationship for the derivative, as well as the values at the origin of the Hermite polynomials. So we're not going to show in this exercise how we can calculate those without making use of the generating function. We're just going to assume that that work has already been done. But the question is, can we now build on that to show that the generating function is indeed this exponential? So in order to get started here, let's have a look at our generating function. Generating function here. We're not going to write here that this is equal to that exponential, because that's exactly what we need to show. Rather, we're going to use the definition here that the generating function can be expanded in a Laurent series to give us the Hermite polynomials. So this we do know, h and x, and then we have t to the power of n divided by n factorial. So what I suggest you do now is pause the video and take the derivative of this expression with respect to x, then make use of the recurrence relation for h and prime, and see if you can somehow massage the resulting expression on the right hand side such that the generating function appears again in one way or another. And hopefully that will give you a differential equation that will help you then to figure out what the generating function should look like. So pause the video and take the derivative with respect to x. Okay, let's proceed. Taking the derivative with respect to x will give us a summation of h n prime of x t to the power of n divided by n factorial. Now h0 is just a constant, so if we take that derivative, that will give us 0. So actually this summation here starts at 1 and not at 0. We also know what this h n prime thing reduces to. So it's summation from n equal to 1 to infinity. And then h n prime is just 2n h n minus 1 x t to the power of n divided by n factorial. Let's clean this thing up a little bit, hopefully in such a way that it becomes easier to bring this thing back into the equation. So one thing that's bothering us a little bit is this n minus 1 here. So let's make the substitution n tilde equal to n minus 1. And if we do that, we get a summation. So if n is equal to 1, then n tilde is equal to 0. So that brings the lower bound back to the familiar 0. And then we have 2 times n. N is going to be n tilde plus 1. And then h of n tilde of x t to the power n tilde plus 1 divided by n tilde plus 1 factorial. The good news here is that we have some cancellation going on here. So we can write this as a sum n tilde going from 0 to infinity to h n tilde x t to the power of n tilde obviously plus 1 divided by n tilde factorial. If we take a look at this thing here and we compare it to what we have up here, which again is our generating function, you see that this is basically the generating function, but multiplied by 2, of course. And also here we have t to the power of n plus 1 rather than n. So we have an extra t here. But then we have the generating function again. So the good news is that now we have something that looks very simple. If we take the derivative with respect to x of the generating function, we should get back that generating function, but multiply this with 2t. So pause the video and see if you can use this information to derive something more about the generating function. So what is a function that if we take its derivative, we get that same function back, but multiply it by 2t? A prime candidate, of course, would be an exponential. So if we have exponential 2tx, if we take the derivative with respect to x, we get back that same exponential, but multiplied by 2t. So that works, but obviously if we take this expression and multiply it by any constant, that would also work. And don't forget, in our case, since we only care about derivatives with respect to x, anything which involves t is a constant for the purposes of taking derivatives with respect to x. So the constant that we have here could actually depend very well on t. So this is the most general form of the solution of that equation here. So now the next step is trying to figure out what this f of t is. What I would suggest you do here is take that expression and substitute x equal to 0 and see if that helps you to finally determine what this f of t is and then also what the whole generating function is. So pause the video and substitute x equal to 0. Okay, let's substitute x equal to 0. So our generating function at 0t is going to become exponential 0, of course. So that's 1. And that's good news because now we've isolated our unknown function f of t. And if we go back to the original equation over here, which is used to define the Hermite polynomials in terms of the generating function, we can here now substitute x for 0. So this will give us a summation of n going from 0 to infinity, Hermite polynomial of order n at the origin, t to the power of n divided by n factorial. Don't forget, we know what this thing is. That was part of our original assumptions. So if you go back to a previous exercise, there you can find that at the origin, if you have a Hermite polynomial of odd order, that the result is basically 0. And if you have a Hermite polynomial of even order, then the end result is -1 to the power of n to n factorial divided by n factorial. So if needed, pause the video again to make those substitutions to try and figure out what f of t is. Okay, almost there. Let's have a look here. If we have odd orders, we don't have any contribution. So the only contribution is coming from even orders of Hermite polynomials. So that would suggest that it makes a lot of sense here to try and make the substitution n is equal to 2 n tilde, because that will allow us to only keep the even terms. Doing that, we have that f of t is a summation of n tilde still from 0 to infinity. And then we have h of 2 n tilde of 0, t to the power of 2 n tilde divided by 2 n tilde factorial. Now we just need to substitute what we have up here, and that gives us a summation n tilde from 0 to infinity, -1 to the power of n tilde, 2 n tilde factorial divided by n factorial. Okay, this is just substituting this thing in here, giving us that. And then, of course, we need to make use of the second term here. Shouldn't forget that one. And then we divide by 2n factorial. Lo and behold, this 2n factorial thing drops out. And now we're almost there. We can just rewrite this thing here, combining these two terms in such a way that we have a power of n tilde there. This actually is a summation of n tilde from 0 to infinity of minus t squared to the power of n tilde divided by n tilde factorial. And we know what that is. That is just the series expansion of an exponential with as argument this thing here, which is minus t squared. So our f of t is exponential minus t squared. And then combined with what we already know here, that our generating function is our f of t times that exponential, well, that finally allows us to draw the conclusion that our generating function of x of t is indeed exponential 2tx exponential minus t squared. So this thing is not as arbitrary as it would seem. You can just derive it from the structure of the differential equation for the Hermite polynomials. So that's nice.